Okay, good evening. Today we will make the class of quantitative research methods, right? I will try to record this for sending to you after whatever we do here. The idea is to train you a little bit in quantitative methods. Okay, research, as you know, is hard. What makes hard research is that it requires patience. Uh, how to explain? There are different kind of researches. One is, as you know, qualitative, where people don't use equations, nothing, almost nothing, or maybe they just touch a little bit of statistics. Doing a survey and analyzing statistics is not quantitative. I think it's still matched with qualitative research. Only doing a few statistics is not a big deal. And we have quantitative, where people manage equations, manage variables, derivatives, etc. Well, when we are going to analyze a problem in research in general in any area, call it physics, mathematics, business, economy, whatever, you have to see what other people did before. No? I mean, you investigate first what people did before you do a research. Sometimes, because I mean, this is a question comes from the students always, and that's why I repeat this, including my students. They told me, oh, there are not only two ways, qualitative and quantitative. Qualitative, we just say words, and quantitative, we have to do a survey. Actually false. I mean, quantitative, not necessarily you have to do any survey, and not necessarily you have to collect data. Not necessarily, because many people have collected data before you. In many cases, and many people have studied probably the same problem you are studying already. No? Then I will put you an example. Let's assume that in this room I elevate the temperature. We have a here. I don't know. Let's assume I can control the temperature of this room, and I increase the temperature to 40, 45 degrees. Let's put 40. What do you think will happen? You will start to leave the classroom. Everybody will start to leave the classroom. And I don't have to interview you asking, why did you leave the classroom? Because as soon as I enter and I feel that the classroom is the hell, immediately I understand what's going on. So, I mean, you have to understand how to connect variables. That's the most important in quantitative research. You have some parameters you can control, some variables you can control, and you have to see the consequences of changes those variables. And sometimes, of course, you require statistics, you require observation, you require things. That for this reason, we will start with the statistics here in this lecture. Basic notions of statistics. I will just ask something naive to see if what is your level of statistics. Let's assume I have a box here. I'm looking at a box here. My this board. Up here. Let me find a better marker. And then I put let's put 10 balls here inside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I enumerate them 1, 2, 3, 4, 5, 6, and so on. I enumerate those balls. And then you cannot see what is inside. You cannot see what is inside. Then I close my eyes, enter, and take the ball. What is the probability of getting the number 5, for example? Who can tell me? Probability of getting 1 divided 10. Perfect. Excellent. 1 divided 10. Getting 5 equal 1 divided 10. And then I have more 5 here outside. It's not here anymore. Then I ask you after, okay, given the fact that I collected the number 5 already, what is the probability of getting the number 3? Number 3. I mean, I got the 5 already. I put the 5 here. outside the box. I cannot see what is inside, and I try again. Next attempt. What is the probability of getting 3? Any opinion? 1 divided by 9. 1 divided 9, because you already took away one ball. The sample space change. Now, this is important. In statistics, we have a sample space. The sample space measures all the possibilities or all the possible outcomes from some specific experiment. In this case, the experiment is taking away the balls. But your experiment could be, I don't know, it depends on what you do. I don't know what kind of research you do. But let's assume that you want to calculate certain probability. Of course, you have to create a sample space and calculate the probabilities based on that sample space. And the probability is a quotient, it's a ratio between the positive events related to what you want to measure divided by all the possible outcomes of the experiment. In this case, when I did the first experiment, which was getting 5, the positive outcome was 5, only getting the number 5. And all the possibilities were 10. Okay, 1, 10. So the second probability was 1 over 9. If I continue, it will be 1 over 8, 1 over 7, 1 over 6, and so on and so on and so on. And then what is I asked you, okay, now I want to calculate the probability of getting 5 and then after getting 3. And I use the word and, this and this, one behind the other. What would you say me? What's your response? You can say you don't have to make the products, but is 1 divided something, but you can tell me. You know conditional probability? Did you study conditional probability before in your career? Well, and don't be afraid that we will not see here quantum mechanics or something strange, because in quantum mechanics, people use amplitude of probabilities, which is different to standard probability, which is what we are saying here. This is classical probability theory. I will not touch anything quantum strange. So is the conditional probability, well, let's put here, the ordinary notion of probability is number positive events divided number of outcomes, all the possible outcomes from a given experiment. In this case, all the possible outcomes were 10. Yeah. Very easy, no problem. When I have this and I asking you probability of this and this, then you have to use the notion of conditional probability. And these probabilities are conditional in this case because the sample space changed. There are many different reasons why two probabilities are dependent from each other, but the formula, let's do like this. The formula is probability of getting an event B given the fact that is or the opposite. Let me write better in the opposite. Getting A given the fact that you obtain the event B is equal to the probability of the intersection divided probability of B. This is the formula of conditional probability. Now, what can you see here? This guy here is the probability of A and B. Intersection. Intersection means and this and this. Union, when you say union, is or this is different. So you have to be careful, because probability, what makes probability difficult to many people is that you have to translate the English, in this case English, or the language, whatever language you use. You can speak Chinese, right? Portuguese, no? Você fala português? No. Okay. Well, any language you use, you have to translate into equations. quantitative observations. Any qualitative data, observation can become quantitative, and I will explain for you to you how to do that when we cover random variable, but we go slowly warming up right now. This is telling me that the probability of getting, let's assume that A is 5 and B is 3. The probability of getting 5 and 3 is the probability of getting 5, given the fact I obtained 3, divided by probability of 3. Or I can do vice versa. If I put here that this is 3 and this is 5, it will be the opposite. It will be the probability of getting 3, given the fact I obtained 5, divided by the probability of 5. In this case, then it will be the product. Probability of A given B, probability of B is equal to the probability of A and B. The probability of getting 3 and 5 is equal to 1 divided 10 multiplied 1 divided 9. So it's 1 divided 90. Something very small. Very small. And if you continue, it will become, well, the subsequent probabilities become larger. The last, for example, if there is only one ball, what's the probability of getting the ball? Of course, 100%. Yeah, for sure, 100%. So, but this is the basic notion of probability. Let's construct some sample spaces. Let me do this. Let's assume I flip a coin. I flip a coin. I flip some coin and I ask you the probability of getting head and tail. What is the sample space in that case? Let's see if I can find the sample here. I can go here. Google with my friend. Right, so command is found. Probability here, tossing a coin. If I toss a coin, I have 50% of getting head and 50% of getting tail. Trivial, right? Well, what happens if I flip two coins? I take one coin, I flip both coins, and I tell you, okay, what is the probability of getting no heads in this attempt? No heads. Then you have to construct the sample space. What are the options? The options are sample space is represented like this. The options are head. You can, the two coins can become head. It could be tail. It could be head, or it could be tail. So the probability of getting no head at all is there's only one possible outcome among 4. So probability of no head is equal to 1 divided 4. 1 divided 4. Right? Perfect. No problem. Now the probability of getting at least one head. How do you calculate that? Probability, let's put it here. Probability of getting at least one head is equal to what? 3 divided by 4. Yeah. Okay, so I can see that you are not that bad in these basic issues of probability. So maybe we can jump to random variable. But before jumping to random variable, let's do a quick revision of this concept here. This is nothing strange, it's not terrible. I think this is clear for you, so I will not challenge you with this. Venn diagrams are these. We have two events. This is an example event. Is soccer. Alex, they like soccer. Casey, Drew, Jay also like tennis. Great, excellent. Well, you can make a union or you can make a intersection, etc. In the union, of course, all the elements appear. But the best way to represent this is like this. Casey likes both. She likes soccer, she likes tennis. Drew is another guy, he likes soccer and tennis. And Alex only likes soccer, Hunter also, and Jay. Then I will ask you the probability that these individuals, some of these individuals like simultaneously soccer and tennis, for example. Then, of course, you have 2 divided by the total, which is 5. Intersection. Intersection means conditional. The condition is this. A intersection B is represented by this. And this represents this and this simultaneously. Both events simultaneously. The union, instead, the union of events is this or this, is more relaxed. The union means everything. Union means all this. But when you calculate the probability of the union, you have to be careful because people have the tendency just to apply the sum. Let's call this event A and this event B, or S and T. S because soccer and T for tennis. Probability of soccer union tennis. It will be the probability of soccer plus the probability of tennis plus minus the probability of soccer intersection tennis. When I apply the union, why do you think I have to subtract this? This one here in this set theory. Soccer union tennis is the probability of people liking soccer plus the probability of people liking tennis minus probability of soccer intersection tennis. Why do you think I have to subtract this? Because when I consider probability of soccer, I consider all this circle here. When I consider tennis, I am also considering this circle, so I am zooming twice. Zooming twice. This area is being zooming twice. This area appears here and here in these two probabilities. Then I cannot repeat it double. I have to subtract. Otherwise, I can get probabilities larger than 1. Remember that the sum of probabilities, and this is a sacred rule, the sum of probabilities, some event, is equal to 1. So if this is all the sample space, this will be 1. There is a chance that this is not the whole sample space, that maybe the sample space is bigger, and only the total probability, including outside these circles, is 1. Then the probability inside the circles is smaller than 1, right? Right. So I think this is not a loss. I will show all the diagrams right now. 1 second. How can you look? Later we come with basic definitions here. This is the set theory. This is the union. These 2 circles represent the union. A union B, as I said before, probability of A union B is equal to probability of A plus probability minus probability of A intersection B. Why? Because when I assume probability of A, I am including this area. When I am assuming probability of B, I include this area again, and I have to subtract because it's assuming twice. It appears twice. That's the reason. The complement, if you have a set of events, the complement space is represented with this letter AC, and then the probability of A plus its complement is equal to 1. is equal to 1. So it means all this is the sample space. A represents the positive events. For example, getting the number 5 or the number 3 or whatever was A for us before. And this, the square represents all the possible options. That's the sample space. We will go to practical problem. A second. One set of events can be contained inside the other. Later you can think it's an example. This is not contained, and these are completely disjoint. Disjoint events, it means they have zero section, they side empty. So these are the total, all the theory you need to know about. So now we can go to some basic examples. Let's go to this example. In a customer survey, all the people who participated use at least one of the 3 products. At least. The word at least means at least one of these, no? At least, it's logic. All 3 products were used by 60% of the customers. 95% of the customers use at least one of the products A and B. 85% use at least one of the products B and C. And 50% use both A and C. How big share the customers use the 3 products? Yeah. Of course, these guys, this is a little bit complex problem because it involves three set of events, not 2 as we mentioned before. But still you can do it. Then all the customers, they use at least one. Of course, the probability of the union of the 3 events is 100%. They say that all the 3 products were used by 60%. So the probability of A, B, and C is 60. The union, it means because all 3 products, it says 95% of the products use at least one of the products A and B, at least. And this is why I was talking to you. At least A or B. It means A or B is the union. When you see the word at least or A or B, that means union. So they are telling you is 95%. The same applies at least 85% here for the union of C. And this is the probability of getting A and C simultaneously, which is 30%. Okay? You can see 85% use at least one of the products B and C. That's why it's the union. And 30% use both B's and B's. So I mean, it's important. It's an issue of language. When you listen A and B, it's intersection. A or B is union. Or at least A and B is also union. The word at least. At least, what's your name? Okay. Dorothy, and you? At least Dorothy or Lika came to class. So it's the union. Or Dorothy and Lika came to class. Both of them really came to class. Yeah? So be careful with this, with the language issue, because it's important. Of course, these examples I will share with you later. So much time. But later we will see some problems. It's better to solve the problems related to random variables. We will come back to this problem later, but in the sense of random variables. The probability of A plus the complement is equal to 1. This is what I told you before. If you have let's put here a square, and you have the element A, the complement is outside. A complement means everything outside the element A. Let's put an example. You consider yourself Chinese people? All of you are Chinese people. Okay, except you and me. Okay, we are 2 non-Chinese here. Let's assume that A, it means Chinese people. And outside, well, outside is everything else. So it means me and her. So I will be here. Liquor is you. And here will be Dorothy, and okay, I will remember later your names, but all of you will be here. All the Chinese people will be here. So, what the probability of you being Chinese this class plus the probability of not being Chinese is equal 1. Can you get it? Probability of being Chinese plus the probability of being non-Chinese is equal to 1. Being non-Chinese is the complement of non-Chinese, of Chinese. Okay, let's put it this way. You have to define the even A, as your positive output. Let's put that the positive output is being Chinese. What is the probability of being Chinese here in this classroom right now? We have 1, 2, 3, 4, 5, 6, 7 persons. If I include myself, it's a small class, relatively small here. What is the probability of being Chinese? Let's calculate the probability of A is equal to the probability of being Chinese. Is equal to what? It's 5. Huh? You are 5. 1, 2, 3, 4, 5. You are not Chinese. Where are you from? Yeah, it's 5. 5 Chinese, no? Yeah, 5, exactly 5. I believe I was confused. Okay. It's 5 divided by 7. Now the probability of being not Chinese is equal to what? 2, we are 2, me and Licker, divided 7. This plus this is equal to what? 1. The probability of A plus the probability of complement is 1. Okay. What happens if I have this probability? If I have calculated probability of A and I just have this probability of the complement, and somebody asks me, okay, now calculate the probability of being Chinese. I don't have to calculate it. I can calculate it indirectly. I can say 1 minus probability of the complement, it has to be the probability of being Chinese. Because of course the superposition is equal to 1. Then of course it will be 1 minus 2 divided 7 equal probability of being Chinese, which at the end gets out 5 divided 7. There is no loss here. I think there is no loss with this. I mean, the trick here is you identify the events, the positive outputs, and all the possibilities. Then let's give you some examples. I think I can find some examples. Well, for doing the examples, I better go to random variable first. Random variable. And with random variable, we can make examples because for you, it's more useful to know. How to explain? It's more useful for you to know random variables and distributions because most likely you will need it for your research, particularly those guys who like to take qualitative research and put it in quantitative. Then random variables. Jump into random variables. I can see your statistics is right. It's good. Random variable, I can assign a variable to any event. I toss a count. We saw that before you were tossing a coin. Cha, cha, cha. And there was 50% getting head, 50% getting tail. But what if I give a value of each possible outcome? If I call 0, if you get a, this is head or tail? This is what? You call this tail. Okay, let's call this tail. It doesn't matter. I will give you 0 if this is tail and 1 if this is head. Then I can ask you, okay, give me the probability. The sample space of this random variable is 0, 1, which is you see here. And give me the probability of x equal the probability of x being equal to 1. The probability of x equal to 1. Who can tell me? Who say me? 1 divided 2, 50%. 1 divided 2. Because there are 50% of chances of getting 0, 50% of chances of getting 1. Let's do it physically. I will pay a coin here. Let's put a coin here. Coins. Coin. There's a coin. One patak. One patak. Do the coin. Tail. There's 50%. I say, okay, it's tail. I will assign 0 to the tails and 1 to the heads. It's not different to any. Let's assume that, let's imagine something more complicated. Let's assume that you are not disciplined students, that this classroom is a circus. It happens in the bachelor sometimes it's a circus. Imagine that you have to scold people and so on. And then I want to quantify that behavior. I want to quantify that behavior. I want to say, okay, I will assign a number to each behavior. How many behaviors you know? Bad, good, and regular maybe. Could be well-behaved, more or less well-behaved, bad behaved, super bad behaved. Let's do like that. Okay. Then I will invent a random variable. I will call it y, and I will put some levels: 0, 1, 2, 3, 4. These are the possible values of the random variable from 0 to 4. And then I will say, okay, if you get 0, 0 means bad behavior. Bad behavior. 1 means, well, this is very bad behavior. This is bad behavior. 2 will be X. This is good behavior, and this is very good behavior. I decided to classify like that. You can transform any qualitative event quantitative. This is what we do in any field of science, physics, mathematics, biology, business, whatever. Or I could say, I could measure the arrival on time or late to the classroom. People who arrive early, I will assign a variable 3. People who arrive just on time, 2. People who arrive late, 1. And then I calculate the probability. How do you calculate the probability of each outcome? 0, 1, 2, 3. You have to collect data. In this case, it's true that you need the data of that classroom. In this case, it's necessary. Then you have to go every day to the class, or every time you have the class, and you analyze the behavior of people. Let's assume that you have a classroom of 50 students. 50 students. There are 50 students. 50 students in the classroom. Marvelous, tremendous, amazing. And from those 50 students, 5 of them behave very bad. 10 of them behave bad. 10 of them behave more or less. 10 of them behave good, and for reaching 50, 15 behave very good. Now I can know the probability for each possible outcome, because 50 students represent 100% for me in this experiment. 50 is the total population. 100%. 100%. Then let's calculate the probability of getting 0. Probability of y equals 0. The probability of y equals 0. I just want to test if you didn't get lost in this because I understand it's complicated that you have to define a variable. Pay attention that this example is not related to this. Forget this one. Forget this one. Actually, we can sit down this for a moment for people not to get confused. And we are here. We are here in this example here. My 50 students is my 100%. So the probability of getting 0, I say five students behave bad, very bad. Then the probability of getting 0 is 5 divided 50. 5 divided 50. So it means 1 over 10. Excellent. Probability of getting 1. There are 10 students who behave bad also. Divided 50. This is 1/5. This same as the probability of getting 2, because it's the same. This same as the probability of getting 3. And now the probability of getting 4. 4 represents the best behavior in the class is 15 divided 50. Three divided 10 should be that. Total should be 100%. 1 plus 1 plus 1. 1, 2, 3. There must be something wrong here. Let me see. 1, 2, 3. This is, because I forgot to zoom this one. Okay, this is, if we zoom everything, this plus this is 4 divided 10. 4 divided 10, this one, this case. 0, the case 0 plus 4 is 4 divided 10. It will give me what? 4 divided 10 is 2 divided 5. Then 2, 3, 4, 5. Everything zooming is 100%. This is a distribution, guys. Sorry, girls. All the classroom is girls today. This is a distribution. So when people, and distribution is the most useful thing you have when you collect data. You need to make a distribution. You can find the standard deviation and the variance of this distribution. Well, the standard deviation and the variance are related. The variance is the square of the standard deviation. The expectation value, you can calculate the expectation value of this random variable, and you can calculate the variance. What does the variance measure? Who can tell me? The variance measure how much the data spread with respect to the mean value. And the expectation value is the average of the thing. Now I will continue with the distribution. You will see this in more detail. So let me do the projection once again. I will delete here. Did you copy everything? Can I delete this part? I will delete this part. Now for distributions, the more, let's say, probability at the most professional level, of course, you can use software, you can use things, but you need to understand how these basic issues, because sometimes the software gives you a number. Using a software is not a big deal, but the software gives you a number and you don't know how to interpret it. And I think this is the biggest problem when you do research. People sometimes don't know how to interpret the results and so on. So let's go here. This is a sample. That is this. Let's define a random variable. I have to count this, sorry. I really was on for a moment. I will switch on the projector. Now it's true that we need it. Okay, here. This example, I define a random, I throw a dice with six faces, and I define a random variable, which is the score shown in top face. So the sample space is 1, 2, 3, 4, 5, 6. The random variable coincides with the possible outcome, so I could calculate the probability of each outcome Very easy, 1 divided 6, no problem. This is the example. The probability of getting 1, 2, 3, 4, 5, all of them is 1 over 6, right? Now, let's go to this example. You have three coins, and I define a random variable equal to the number of heads is the random variable. So it means when I flip 3 coins and they fall, if I get 1 head, x is equal to 1. If I get 2 heads, x is equal to 2. If I get 3 heads, x is equal to 3. Why? Because I decided to define arbitrarily. The random variables are defined arbitrarily. You define it arbitrarily. You can construct the sample space 0, 1, 2, 3. 0 heads means all of the output was tail. Then you have to construct the sample space and calculate the probabilities and so on. No problem. That's an issue. This is the sample space. The sample space, 3 heads. You can obtain 3 heads. You can obtain 2 heads here, 2 heads here, 1 head, and 1 head, 1 head. Again, there are 3 heads with 1 head and 3 tails. So 1 head. So what happens if I ask you, calculate the probability of x equal 1 here, this experiment. Probability of x equal 1 in this event. When x is the number of heads, what would you do? You construct the sample space first. And let's find the results where if 1. 1, 2, 3. There are 3 positive outcomes, which give you 1. So it's 3. Divided by all the possibilities. How many possibilities we have here? Let's count it. 1, 2, 3, 4, 5, 6, 7, 8. 8. So the probability of getting s equal 1 is 3 divided 8. Yeah, and the same with the others. The probability of getting x equals 0, there is only 1 chance, so it will be 1 divided 8. The probability of getting 2, how many events, positive events has 2? There are 1, 2, 3, also 3. The probability of getting 2, for example, is also 3 divided 8. And if I continue x3, x0, whatever, I can calculate the probability. I have my distribution. I can calculate the expectation value and the variance. I will show in a moment how to calculate the expectation value. But in advance, I can tell you that the expectation value, without looking into the book, the expectation value of this distribution is simply the value of each variable. For example, the first variable times its probability plus the second value of the variable times its probability plus blah, 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 the same. So it means, for example, you multiply 1 times 3 divided 8 plus 2 times 3 divided 8 plus the other variable times the probability plus. At the end, the final result, the total sum is the expectation value, average. This is called weighted average. Weighted average. I think you know what is an average. For example, if I have 1, 2, 3, 4, 5, 6, and I tell you, calculate the average of those numbers. 1 plus 2 plus 3 plus 4 plus 5. But what happens if the number 2 repeats 3 times, the number 4 repeats that? Then you have to multiply each number by the corresponding repetition number, the number of times it repeats. And this gives you the numerator, and you divide by all the possible outcomes. Anyway, I will share these materials with you. I will send it to you later. This is another example for the dices, etc. Now, let's calculate this example. Look at this. This is some kind of game. I don't know if you have played this. Well, this diagram shows a spinner made of a piece of card in the shape of a regular pentagon with toothpicks. So it's centered. The 5 triangles are numbered from 1 to 5. Each time, blah, blah, you can get any number. If X represents a number on the edge, what is the probability of getting 4? Here. Assuming that all of them has the same probability. B, 1 divided something. Because there's only one chance of getting 4. And how many chances are? It should be this. 1 divided 5. Because there are 5 possibilities. Anyway, you can play with these things and so on. Well, pay attention, random variables is a very useful tool in quantitative analysis. I will just go quickly to here because we don't. We saw a little bit of conditional probability just now. Before going to the decision trees, since we are in random variables, which is this chapter, I will skip a little bit. I'll show you a few things. The expectation value. This is what I was talking to you. When you have a set of random variables, the expectation value is the product of each outcome multiplied by its probability. And then let's do an example about how to calculate the expectation value of this. Let's toss one dice. This is the example of tossing one dice. The probability of getting 1 is 1/6, the probability of getting 2 is 1/6, the probability of 3, 4, 5, 6. This is an example of the expectation value. You multiply each output for its probability, and at the end, you take 3.5. Let's do it with the coin. When I toss a coin, I have two outputs, 0 and 1, right? For example, the probability of X equals 0 is 50%. Probability of X equal 1 is 50%. Then what's the expectation value then? You're assuming that this is there and this is head for the random variable, a coin, tossing a coin. Okay, let's calculate the expectation value. Yeah. Expectation value of this variable. It will be 0 multiplied by 1/2 plus 1 multiplied by 1/2. It will be 1/2. For example. Then, I mean, it's not difficult to use this formula. It's not difficult to use this formula. But of course, you have to get familiar with the language and so on. Look at this example. X is the number of items that a randomly selected customer buys in a special shop. We assume the following distribution. Probability of X equals 0, 0.3. So 0 items. For one item is 0.2. I think there is an error here. This should be 3. It should be 3. 1, 0, 1, 2, 3. 0, 1, 2, 3. 0.1, 0.4, 2.2, 0. Well, this book has some errors. Actually, it's not the first time that this book has some error. So if you look 0.1 and 3, so it should be 3 here. This is not 0. This book is wrong. This should be 2. Or 2 here, not 0. This is equal 1, and this is equal 0. Now it's correct. It's a typo error. I think this textbook has error. But if you understand the concept, you will find the error. Then 0 multiplied by its probability is 0 times 0.3. 1 divided multiplies probability, 1 times 0.2, 2 times 0.4, 3 times 0.1, and this is the expectation value. What does it measure the expectation value? If I have a distribution, I am plotting the data, X, and this is the probability of X. Then I have 0, 1, 2, and 3. 0, 1, 2, 3. The probability of 0 is 0.3. Let's put it 0.3. 1 is 0.2, 0.2. 2 is 0.4. And getting 3 is 0.1. And 0.1 should be here. You can make a histogram, which is a powerful tool for analyzing data. Histograms and mathematics. I think you have seen this figure before in your job or something. No? This kind of histograms, charts, etc. The histograms can be also circular. You can have a circle, each portion represents a percentage. Okay, some percentage. So the expectation value 1.3 means 1.3 here. So the average of this data is this point here. This is what it's telling me. If I find the variance of the standard deviation, it's telling me how much the data value. Any questions? Any doubts right now? Questions? Comments? No? Okay. Right. Yeah, unfortunately, we only have this session. Of course, I can't go so much into details. So I will have to jump a little bit for the variance. The standard deviation, of course, let's put here. The variance of this of a random variable of a distribution, it will be the expectation value of this difference. This is the random variable, this is the expectation value, a square, and the expectation value of that. There are two formulas for that. This is one of the formulas. The second formula, well, derived from the first, is this one. Some people prefer to use this formula than the other. The variance is the expectation value of x squared minus expectation value y, because let's assume this data here, this example, we assume that x is a random variable with values 2, 4, 6, 8. And the distribution is probability of 2 equal probability of 4, probability of 6, probability of 8 equal 1/4. What is the expectation value of this? You have to multiply each value for this probability. 2 multiplied by its probability, plus 4 multiplied by its probability, plus 6 multiplied by the probability, plus 8 multiplied by probability. This is the expectation value, which we showed before. And this expectation value is what you will replace here. So in this case, 5. You have it for finding variance. The variance will tell you how much the data deviates from the expectation value. But I have to find this. For finding this, I have to put the variables squared. So it's like finding the expectation value, the same expectation value, but now squaring this. Then I will take each number, and I will square it. They did it different here, but you can do it this way. But we can do expectation value of x squared. Let's do it. It could be 2 squared multiplied 1/4 plus 4 squared multiplied 1/4 plus 6 squared multiplied 1/4 plus x squared multiplied 1/4. And this gives me this number there. And I just replace and I obtain the variance. And what does it measure the variance? How much the data is spread around the mean value. Then the distribution is complete when you have the expectation value and the variance. Because from the variance, the root square of the variance gives you the standard deviation. And the standard deviation is what tells you how much to the right and to the left with respect to the mean value the data is spread. If the standard deviation is large, it means you cannot trust so much. You cannot trust so much in the mean value as an indicator. For example, let's talk about the this utility theory, which people use in marketing sometimes. You remember, I don't know if you have seen that, but well, sometimes people use the expectation value for taking decisions in companies, in daily life, whatever. But the expectation value is not enough. You need to know how much the data is spread around the expectation value. And that's what helps you to make a decision. Yeah. What I did just now, I will tell you this part. This is what I just did just now. 30. So the variance in that case, it was 30 minus 25. I think it should be 5 because it's 5 squared. Yes. Yeah, it's 5. We'll say this 30, 5 squared, 5. This is the variance. So when you have the distribution, have this. You have a mean value here, some number, watch 1.3, Then and you have the variance which tells you how much the data is spread expectation value. And that's very important because you girls, you are probably interested more in collecting data and collect qualitative data probably and converting into quantitative. And this is the way. Promote the data to random variable, and that random variable gives you a distribution. It's a good starting point. And then after you can think in using a software, this kind of things. But first try to understand this concept, advance. Now let's close the distribution. There are many different distributions, but the most important one, the Gaussian distribution or normal distribution. This one, I will not go so deep. You can use tables from the textbook, but you can also use a software to calculate. But the standard distribution, normal distribution, behave in this way. And it comes out empirically. Some people in the past realized they collected data and they realized that when the data is too large, the data behave in this way. It has 0 expectation value and it has a standard deviation equal to 1. The standard normal distribution. There is a normal distribution which is not standard with sigma squared different to 1. This is the variance. And the standard deviation is plus minus 1 because it's the root square of it. This is the expectation value. This distribution is useful when you deal with random variables which are continuous. Continuous in value. I said 1, 1.3, 1.2, 1.2, and there are infinite numbers between each value. Continue data. In that case, this distribution is the most useful. Or when you have an infinite amount of observations, a large amount of observations. We also have the Poisson distribution. We have the binomial distributions. Well, I can go so deep into each distribution. Each distribution has its own reason for the existence. But in this case, for example, I will tell you that if I ask you what's the probability of getting x equal 1, you have to say 0. It's almost impossible that you get a single number as an output in this distribution because there are infinite amount of numbers between each pair of numbers. Between 1 and 1.1, there are infinite amount of numbers. For example, 1.0000000 something is in between 1 and 1.1. And you can put an infinite amount of numbers. So the chances of getting a single digit here is 0. So if somebody asks you, probability of 0. What you can calculate here is intervals, probability of getting intervals. Then you can come here, the probability of x to be between 0 and 1, for example, then I have to, it's represented by this area and it has to be calculated. There is an integral representation of this, which you will not learn, because in reality, if we are going to be rigorous, I will say the probability of getting some interval A, B, is the integral between A and B of the density of the probability dx, and this minus x squared with something here. But this, guys, this is not necessary to calculate this probability. This is the concept, but not the tool. There's some software, I recommend one particularly just now. So Wolfram Clouds. Many physicists, mathematicians, statistical, business, whatever they use. Well, it don't work. You can create an account for free, sign in, and then forward it. We don't have time for going into the software, but I recommend it because it's free, it's a free resource, and you can make statistics inside it. And only statistics, but normal and data analysis and many other things. So I can send you the instructions about it later. Here also you can calculate, for example, the normal distribution probability of x between -2 to 1, which is represented by some areas here, this curve, etc. The expectation value 0 divides 1 areas probability. But there are cases where the normal distribution is not the standard. In this case, for example, this is a normal distribution. There are two normal distributions here. This one is fatter than the other. One is taller than the other. The total area below this curve here is 1, because the total probability has to be 1. And the total area of this one is also 1. Probability. This area is equal 1. And this area here is equal 1. Because the area measures the probability. Then if I tell you, okay, look, this sigma is 0.6 and sigma is 1.4. This guy has larger standard deviation than this. Then let's assume that we are doing an observation. Obviously, the expectation value here is the expectation value of this distribution. Okay. This is not the standard normal distribution. To this one, you call it normal distribution, not standard normal distribution. Then let's assume I ask you here naively, in which distribution do you trust more? For example, if I am trying to observe for concluding that x is equal to, do you trust more this distribution or this distribution? Let's assume that you get this, or you can also get this. What is the difference between these two distributions here? They have the same expectation value. They have the same expectation value to them. What's the difference? Which one is more accurate, let's say, accurate? This one is narrow. It means that most of the data is almost centered around the expectation value. Of course, if somebody tells me that they have observed this value consistently in the experiments and the data only deviates a little bit like that, okay, I trust a little bit. The limit of this variable, when this tends to 0, when it becomes very thick, is a delta Dirac distribution, which you will not see in this course. In this course, you will not see that, because it's too advanced for you right now. But I know, you don't know, I know. Well, it's normal because it's my field. Now, for this case, the data is widely distributed around the expectation value. So in this case, you cannot trust so much you cannot make so much conclusions based on the expectation value of this distribution here below. In this one, you can trust a little bit more in the expectation value. So this is important when you analyze data. Expectation value, standard deviation is everything in the distribution. Now let's jump a little bit to correlations, because this is until 9 p.m., right? This class finished at 9 p.m. 9 p.m., right? Yeah, so we don't have to take break. I don't need a break. If you don't need a break, I don't need a break. Okay. Now, there are cases, guys, let's put it this way. I will connect many things simultaneously for saving time. Let's assume that you want to, let's go to an example of daily life. Airlines, because I was talking about that today precisely to some people, how the airlines manipulate the prices for the customer. I mean, you understand what I say? Airlines, you have price of the ticket, and you have demand, right? There is a relation between price and demand. When the airline increase the price, something happened to the demand, and vice versa. What do you think? Yes, there is a relation. When the airlines increase the price, the demand decreases. Because, of course, let's assume in a hot season, you're in a hot season. Hot season, summer is the hot season, right? Many people want to travel in summer. The airlines, they know, clever, very smart. What do? Increase the price. Well, if they increase the price too much, nobody will buy those tickets. Nobody will buy them. Then they manipulate a little bit, they increase until for reducing the demand up to the level that they can fill the plane. They need to fill the planes. Because if they don't fill the planes, they lose money also. So this is a case where two variables are connected. Now I will put another example. Another example of how variables are connected. The temperature or the season versus the amount of people going to a beach. When it's winter, how many people go to a beach in winter when there is snow falling? Almost zero. Who goes there? Nobody. You will not go to a beach in winter. Well, some people might go, but most of the people don't go, especially if there is snow. So the variable temperature, or let's call season in this case, is connected with the amount of people going to a place. For example. So for connecting variables, connecting different variables, we have certain techniques. And the most popular, of course, is regression. You collect data and you make regression. You have done regression before, I am sure. In Excel, you use Excel for doing regressions. You use Excel, yeah. Some of you have used Excel some time in your life. I am really surprised if that's not the case. In Excel, you have realized that you can plot the data. You can plot the data. Now we are not talking about this distribution, but let's assume you have the data like this. You collect data, there is a variable x, y. And when you are going to make the regression, Excel gives you some options, no? Like linear regression, quadratic regression, any regression, and even give you the equation. No? You cannot extract the equation from Excel. You cannot find the equation. In this case, it looks like a linear. It doesn't have to cross exactly the points. It doesn't have to cross the points exactly, but the tendency, the general tendency of this figure is to be a straight line. And there is, of course, there is an uncertainty. Each value, okay? And there are ways to do this. Linear regression is the most popular, of course. This is a case of linear regression where you obtain this figure, y equal the slope times x plus 1 cut. The cut in this case is 0, but it could perfectly be different from 0. These quantities can be obtained, and there are standard methods. I can share with you the slides or the copy of those methods. But for the moment, what I can tell you is that you can calculate, and in most of the cases, You don't have to do it by hand. You can use a software for calculating that. But the important is tendency. Now, if you try to be too accurate, you make a mistake. For example, let's assume that you are not happy because this line doesn't touch all the points. No, it's disaster. What's this? And then you try to make accurate and external line, you say, oh no, I want the figure to touch all the points, and then you try to do something. It becomes a mess. And this is an example of what people call overfitting. No? It doesn't display the average behavior, the tendency of the data. So the tendency is that y and x behave linear. Now, there are small fluctuations, but the nature of those fluctuations require further investigation. What you care in most of the cases, broadly speaking, is the tendencies. How one variable behave with respect to the other. If one variable increases, the other has to increase also, or decrease, or how is that dependence? They behave linearly, quadratic, exponentially, logarithmic, etc. Sometimes it comes out, and by experience I can tell you, that y and x are not related linearly. But it comes out that the natural logarithm of x versus y is linear. It's a straight line. Then you will have something like y is equal to a constant times natural logarithm, something like that. Then you can say this a can go here, and then you can say exponential y is x to the a, and you can play with the equations, etc. Well, I mean, what I'm telling you is that there is no unique technique for watching what is the tendency between different data. Statistically, we can investigate the correlations between variables. There are techniques for analyzing, and there is a quantity which helps to measure that, and I will show you right now. We were watching just a few seconds ago. We were watching the random variables, right? But there are distributions with two different variables. They are called marginal distributions, or two or more. And the idea is to see if those variables are connected. And I think this is very useful because one of the biggest issues in research is to see if the variables are connected. You can make a hypothesis. Let's assume you make a hypothesis. You say, your hypothesis, if I decrease the price of the chocolates, more people will buy chocolates. This is your hypothesis. And then you say price of the chocolate versus amount of people buying chocolates. I decrease the price, and I can tell you that more people will buy chocolates. And then you say, it should be something price, proportional, once, or vice versa. Number of people buying chocolate, one divided by the price. I decrease this, I increase it. Something like this. When this decreases, this increases. Number of people. Well, it comes out that in the practice, maybe it's not like that. Maybe people will not buy chocolate anyway because they want to keep healthy. There is a chance. There is a chance that many people are getting diabetes in an area and they are afraid, whatever. There are plenty of reasons why this is happening. So you can make a hypothesis, but then after you see the data, and then you have to see if really that correlation exists. And there are ways to test that. And I will show you in a moment. Those in a few seconds. After, I will share this book with you, right? Because it's important. We have this called joint distributions. Joint distributions. So regressions and joint distributions have to be worked together. They have to be worked together in parallel. Let's say when people say, I would say this is not arrogance. It's not arrogance because people misinterpret confidence with arrogance, and it's completely bad. And sometimes people hate you because you are confident, but it doesn't mean arrogance. Let's put an example. You give me some data. You give me this data like this. Let's put the revenue management in airlines. Price versus demand. Price, and this is the demand. Demand And this is price. Excellent, wonderful, magnificent. I know for intuition, I don't have to be a genius for knowing that when the price increases, the demand decreases, then and vice versa. Then in the case of the ticket, no? So it should be something like this. You plot the data, will give me something like this. It will not be difficult statistically to find a correlation between these two variables. I could make a marginal distribution if you want, etc. But what I want to remind is that if you are good in mathematics, if you are in statistics, if you have your brain very well trained quantitatively, you are able to see what kind of model match with the data, even if you don't do the analysis. Even if you, I mean, sometimes it comes out, there are guys who approach to me with data, they put the data on the desk, and they ask me, okay, can you help me to analyze this data? And I say, this is this function, blah, 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 blah. Save hours and hours of work. Why? Because it comes out that in nature, many relationships between variables behave more or less the same. And this is what happened here, for example. This happens in many systems, in a harmonic oscillator, in a pendulum, in price-demand relationships. There are many systems which behave the same. Then you can take advantage of that for analyzing, and you save plenty of time. And then you start to analyze. Wow, magic! You have many conclusions. The most advanced your techniques are, more information you can extract from the data. Okay. So let's go to joint distributions. After joint distributions, I will explain a little bit about matrices, arrangement of matrices, linear algebra, because it's important for analyzing data, eigenvalues, and vectors. But there's no time for covering so many things, so I will just mention naively a few things. In this kind of joint distributions, of course, I mean, you have some questions. I don't know who is your supervisor because you are all involved in some thesis. This course is called research and methodology or something like that. You are involved with a supervisor doing something which I don't even know what you are doing. I hope this information is useful. But any question you have outside, even if I don't supervise you, is welcome. You can come and ask. Now, look at this. This is a random distribution, random variable distribution, and it has two variables now, x and y. And these are examples. Okay, this is what people call marginal distribution. You can have values for x, values for y, and so on. When you sum all the possible values of y, you are calculating only the probability of x and vice versa. And there are ways to calculate that. I think you can study this part by yourself. But the point I want to remark here, the expectation values, etc., is this quantity. This is what I wanted to show. This quantity is called covariance. Covariance between x and y. This is what measures the degree of correlation between two variables. If I have a variable x, for example, let's put an example, price could be price, and this could be demand. Then I want to see if they are really correlated in some system. Then I calculate the covariance like this: expectation value x minus expectation value of the first variable times the variable minus expectation value. So it's the expectation value of the expectation value. So there are two expectation value of x here, one expectation value of y here, and the difference with the variables, expectation value. So one example is below. This book is very clear because they do many examples. But there is an issue with the covariance. Is that it's not good measure because the covariance has units. Then when you don't know whether the covariance is large or small. I mean, for knowing, I will give you an example. 50,500 kilograms is large or small? 500 kilograms, large or small mass? 50 kilograms is large or small? 100 kilograms is large or small? Depends. If I compare to other units, they look large. So there is no way to know whether it's large. The only way to know whether some quantity is large or small is using the coefficient of variation, which is the covariance divided by the root square of the variances of each marginal distribution. And this number is between -1 and 1. If this -1 is telling me that when one variable increases, the other decreases perfectly. If this number is 1, it tells me that when one variable increases, the other also increases perfectly. When this number is 0, there is no correlation between the variables. Your hypothesis of correlation is wrong. You cannot assume that correlation. Unfortunately, in this class, I will not give the lecture on hypothesis testing because there is no time. I think it's already 30, and we have to see other things. But you should know that this formulation exists. Well, for example, if it's 0.5, it's 0.5, it means these variables are partially correlated. But the correlation could be partial for many different reasons. Maybe there is a third variable, an additional variable, which you are ignoring, which also is correlated to these two variables. And it makes your experiment not to be so perfect. You are not controlling that variable. Let's put in this example. This is the classroom. I have this classroom here. I can control the temperature. I control the temperature. That's one variable, temperature. You can call it parameter or variable. I can control the lights, the intensity of the lights. What else I can control? The volume of my voice, etc. Let's assume that I want the correlation amount of people versus the light, the amount of people in the classroom versus the light and the temperature. So I have three variables: light, temperature, and amount of people. Then I find that they are correlated. When the light is 0, there is no light, there is no there are no people here. When the temperature is too high, there are no people here. There is correlation between those variables. But maybe that correlation is not perfect. And you know why? Because maybe I'm ignoring another variable. Is the volume of my voice. What happens if I start to shout and become crazy and start to throw things here? People will leave the classroom also. So probably the partial correlations between some set of variables could be a natural consequence of the fact that you are ignoring one more dimension or one more variable which should be there also. And for this purpose, methods like dimensional analysis are useful. Dimensional analysis, I will not cover it here because it will be too much. But you should know that when you formulate an equation and you make a regression, for example, y is equal x squared a plus bx, and this is one of your variables you measure, and this is the others. When you calculate the units of this quantity, they have to match with the units of this quantity and with the units of the dimensions. If this is in kilograms, this combination has to be in kilograms. And this combination has to be in kilograms. And let's assume that no x, this is kilograms, the units of this is kilograms, and this is kilograms squared, or let's put meters. X is measured in meters, that will be meter squared here, and this will be meter. So it means that A has to take the corresponding units for canceling m squared and b kilograms. A should be then in kilograms divided meter squared. And this should be in kilograms divided meter. So I mean, one way to verify the equations is to see the consistency of the units also. Left-hand side has to be consistent with the right-hand side in units. You cannot mix chickens with cats. Number of chickens here, this combination has to be number of chickens, and this combination has to be number of chickens. Number of cats, number of cats. So the same units. By units, I mean kilogram, or the length, the mass, the time, the amount of people. Amount of people has no units. It's just a number. But then it means dimensionless quantities have to be consistent with other dimensionless quantities. The left-hand side of the equation has to have the same units of the right-hand side of the equation. You have to be careful with that. At the moment of analyzing data, it's a common mistake between people. When you analyze data and when you are going to make a plot, let's assume you want to make a plot somewhere. Some people made the mistake, and this is common because I read the thesis in USJ sometimes, and you have the plot and there is no description of the plot at all. People don't make a description, they don't say anything, the figure. And second, the units, they forget to put the units. I mean, you have this figure like this, X and Y, and X, Y is what? What are the units of this? Meters, seconds, whatever. And here also, what are the units of this? Centimeters, money, dollars, what's that? And that's important because this marks the consistency. The consistency. Then it could be the case that Y is proportional to X, but the units are different. The units of Y are different to the units of X. Then you have to find a constant. You have to fix a constant, which may both sides to have the same units. In other words, let's assume that this is in kilograms, but this is in meters. Then A will take the units of kilograms divided meters. And A can be calculated with the data. Then this is very important. I mean, the consistency of the units, etc. Since you are not that strong quantitatively, of course, we cannot go to neural networks or something strange because it will be quite complicated. About linear regression, I will not go so much deep because anyway you have Excel and you can use Excel. Now I want to go to matrix. Because this is very important, matrices. First size called one. Matrices, you have used matrices in your life abroad, you have not even realized that you use them. Matrices are arrangement of numbers. Though they are arrangement of numbers like this. See, well, and what is this? What is this? These numbers? Whatever you collect. I don't know what kind of data you collect, but whatever you collect is these numbers. It could be money, it could be number of people, it could be whatever you want to say. Whatever. We will see an example in a matrix is an arrangement of vectors. This is a column vector, is a column vector. All this could be a row vector. You have seen vectors before, vectors. In your high school, in your primary school, in your, no primary, no, I think primary is much. In your high school, in your university, bachelor, I think you saw vectors. We will not see vectors here. But vectors are to be very important also for analyzing certain situations. Matrices, you can assume matrices. For example, if you collect data, this is different to what you do in Excel. In Excel, you have a column, columns and rows. Columns and rows. In Excel, you accommodate the data in columns and rows. And you have done that the whole time, but you have that what you were doing is linear algebra the whole time. The matrices can be zoomed. Each element, 3 plus 4, 7, 8 plus 0, 0, 5 plus 1 is 5, 6 minus 3 can be zoomed, they can be subtracted. And they can be multiplied by a constant. When you multiply a matrix for a constant, you have to multiply each element, 8, 0, 2, minus 18. This is, the matrices help you to compactify data sometimes, and help you to analyze the axis where that data is concentrated. I will tell you how in a moment, but I think that part will be so hard for you that I'm thinking a very easy way for you to understand that part. A very easy way for you to understand that part, because it's not that trivial to get it, especially if you don't have quantitative background. The matrices, they have inverse. For example, when you divide numbers, it's not correct to write the matrix like this. In reality, in matrices, when you divide, you have to multiply by the inverse. The matrix, one matrix multiplied by inverse is the identity matrix, which is a matrix of diagonals 1, 0 everywhere else. This is the identity matrix, etc. Well, what I want to say is you can compactify data this way, and let's go to another determinant. Matrices, well, this example. This is an example of the matrices I used to. This is what I wanted to find. Look at this. One local shop sells 3 types of pies. Apple pies, they cost $3. Cherry pies cost $4. Blueberry pies cost $2. And this is how many days? How many they sold in 4 days? Monday, Tuesday, Wednesday, Thursday. They sold 13 on Monday, 13 apples. Now, these numbers are the amount of apple pies that they sell different days. And each one, of course, you know the price, so you can ask. What does it represent this dot product? For example, when I multiply this times this, 3, 4, 2, 13, 8, 6. This can be represented more compact in a matrix form like this. This is a vector representing the prices of each product, product 1, product 2, product 3. I forgot already the names of the products, but and this represents the days of the week. I think it's Tuesday, blah, 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 blah. Yeah. And then you can multiply this times this, and you obtain the total amount of sellings. So they sold $83 worth of pies on Monday, 63 on Tuesday, blah, blah, blah. Monday, Tuesday. So, I mean, this is one way for you apply matrices. You can apply matrices for your daily life. You apply this. You use, I think, in Excel, you can do these calculations. Well, in the software I told you also, you can calculate that. This calculation is not difficult. It's multiply 3 times 13 plus 4 times 8 plus 2 times 6 gives you 83. Then subsequently, you come with this and multiply this one. It's 3 times 9 plus 4 times 7 plus 2 times 4 gives you this. And so on. And then multiply this column again with this and this again. But as I told you, you can put this in a software, and the software can help you to calculate the matrices. And now the advantage of using matrices in this case, it will become evident in a moment. But I don't think you need determinants. I think let's go to some questions here. But I think you don't have to go to so much in detail. Or in this case, in this particular case, you have one vector representing product. You multiply by one matrix, which was this. It was 13, 9, 7, 15, representing Monday, Tuesday, Wednesday, Thursday. And this gives you some result, give you another vector. Well, it could be the case that you have one matrix multiply a vector and give you another vector here. And so, and if I want to solve this, I have to calculate the inverse. I mean, these are tricks With the time we have, we cannot go so much in detail. Well, these are tricks which are very useful at the moment of analyzing data. You don't have to do it by hand because some matrices, normally the data you collect is huge. Well, let's summarize this session saying that you can arrange the data in matrices in like what you do in Excel the whole time, and you can do calculation. And once you have the data, then you can do something interesting, which I will show you. That's a way, but this example is not that good. Let's put it this way: you have actually why you only have one session of quantitative analysis. Well, anyway, let's put here why. You have the data distributed in this way. And then you have some vectors representing this, some matrices representing. I will show you an example. For example, this picture is represented by a huge matrix representing the pixels of the picture. It's a huge matrix. So I can find the axes which make this data symmetric. Let's say I can find the axis such that if I rotate this axis here, and maybe the x somewhere, this data becomes symmetric with respect to the pair of axes, some pair of axes. And that symmetry is very important because it tells you more or less how the data behave. And that's where the concept of eigenvalue and eigenvector comes. When you have this matrix here, but this example is not so good because I give you the value in advance. Let's do it this way. You have -6, 3, 4, 5. The guys who study data analytics in advance, they know how to calculate the diagonal version of this matrix. This matrix is called A. I can find a diagonal version of the matrix, which has eigenvalues lambda1, lambda2, 0, and 0. And there are ways to calculate these two values from this matrix. I will not teach you how to calculate because it's useless for you at this point, but you should know that they exist. And associated to this value, there are two vectors or more. I mean, if there are more lambdas, more eigenvalues, there are more vectors. We have vector 1, etc. These vectors give me the directions with respect to which the symmetric. And that symmetry with respect to the data is important because I can then understand the tendencies, some tendencies for the data. But this part we will not cover so much. Most likely in your thesis, you will not use this part. I think in your case, probably most likely probabilities, correlations between variables and regressions. Most likely is what you will finish using. So let's now we have only 10 minutes actually. So which part was confusing, which part was clear? Probability is clear, right? The part of probability is clear. Conditional probability is clear. Random variable was okay. I will share with you the textbooks anyway. I will send you the information. Linear regression, you don't have problems with that, no? Regressions. Well, I will show you quickly this last time something about linear. simple definition here. You can see you have data here. About the matrices, just keep that in mind. You will not use that. Well, if you need some theory of matrices for analyzing your data, you can come to me and I am happily helping you. Look at this. You collected this data. These points are the data you collected somewhere. There is a variable and a variable. Data, data. And you want to make a linear regression of this line. Of course, you use Excel. Well, let's see how this works manually speaking. Your hypothesis is that the data will follow this tendency, this trend. This is the predicted value of the variable y. You have to calculate A, which is given by the average value of y minus b times the average value of b. Average value is assuming all the values divided by n. For example, let's give an example. Let's assume that x, you have the data x and y, like 1, 7, 3, 10, 4, 12, 5, 15. And you want to find the correlation between these two set of variables. This is a single observation. This is a single observation. This is a single observation. They represent the points of the data in the figure. Let's put it here. Represent these points here. These blue points you saw in this figure. And now let's put it this way. You can calculate this expectation value, the expectation value of x. 1 plus 3 plus 4 plus 5 divided 4. The expectation value of y is 7 plus 10 plus 12 plus 15 divided 4. And this is what you introduce here for calculating A. A is the cut of the line you predict. But you have to calculate B. And for B, you have to find the correlation between X and Y, which is defined in this way. This is symbolic. I don't know if you are familiar with this symbol, but this is summatory of each value. First, I will give you an example. It's like taking 1 is the first value of X. 1 minus the expectation value times 7 minus the expectation value plus 3 minus the expectation value times 10 minus expectation value, blah, 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 blah. You do this summatory here. You do this summatory of this, and you obtain the value of B. And then at the end, you have the linear regression. These are trivial formulas. If you want to understand them deeply, you can come to me also and ask me in more detail, because I don't think 2 hours is really enough for understanding all the quantitative results. Unfortunately, we will not be able to cover optimization, which is a very useful topic. But I will just mention, naively speaking, right now, optimization is when you are familiar with calculus, how good is your calculus? Huh? It's good about your calculus. Chapter 4 of this textbook teach you optimization. Let's go to the chapter 4 quickly here. Optimization is one. For example, these kind of problems are very useful because let's assume you want to calculate the revenue management lines and you want to calculate how to maximize the profit of a company or so, or if you want to maximize some area for a construction or whatever you want, depends on if you make engineering or not. Let's go to one example and you will know what I'm talking about, and we'll close this session because we only have 5 minutes. So you can see that this is a collage of many quantitative methods. Once you have the correlation between variables, X and Y, or whatever, you can apply optimization. How is your calculus? Derivatives, you remember derivatives, integrals, this kind of things? Or... Well, anyway, look at this. A homeowner has $320 to spend on building a fence around a rectangular garden. The size of the fence will be constructed with a wire fencing at cost of $2 per linear foot. The fourth side will be constructed with wood fencing at cost $6 per linear foot. Find the dimensions of the area of the largest garden that can be enclosed with $320 more fencing. So this is my constraint, $320 of fencing. And look at the fencing here. This one, this side, costs $2, $2 per linear meter. So I can create two variables, X for this and Y for this. So the perimeter, I can calculate the area. The area of this fence is X times Y, and the cost will be the perimeter multiplied by the corresponding one. Then will be, the cost will be 2x here, 2y, 2 times 2y, plus 6 times x again, because x is there. So I have this equation and I have this equation. Whenever I have this kind of constraint problems, this is an optimization problem. In economy and finance, even in any other area, physics, mathematics, we always deal with problems of optimization and you don't realize. For example, if I want to calculate what is the fastest route from here to Praça Pereira Amaral or to Gran Lisboa, the casino, that's an optimization problem. Because I want to find what is the route which minimizes the time for me to go there. That's an optimization problem. You can apply these techniques. Normally, you have a set of equations. One of the equations represents a constraint, and remember, this constraint is $320. That's why they put here $320. And you have this. And the idea is that you solve one variable here. For example, this, you can compare 2x plus y equal 320 divided 4, okay? Which is 80. Then you can solve for y in terms of x and you replace here. Then at the end you obtain, since it's solved here, I will not do it myself, I will just show you the result. This is the equation I am talking about. This one. This equation becomes this, and then you replace in the area. Now the area is a function of a single variable. Then you calculate the derivatives of this. Derivative of the area with respect to x equals 0 give you the extreme values. Critical values. It could be maximum or minimum. And the second derivative tells me whether it's larger or more than 0, tells me whether it's maximum or minimum. That's why you see these guys, they calculate the derivative here, 80, for solving to x. So x equal 20, they obtain. When x equal 20, there is a possibility that the area is maximum. When x is equal to 20. How do you know that? You calculate the second derivative. The second derivative of this is smaller than 0. And you should remember from your calculus, if you see calculus, that when you have a function with a maximum here and a minimum here, in critical extreme point, you have f dx equals 0. You have df dx equals 0. In this case, dA dx, because it's dr, dA dx. But in this case, when it's maximum, the second derivative of the function with respect to the same variable is smaller than 0 because the slope change. The slope change from positive to negative. Remember that the derivative measures the slope of the tangent line to the curve. It's something general. It's a result from calculus. And in this case, the second derivative of A with respect to A is larger than 0. So when you calculate the second derivative here, it's clear that it's negative. So this is a maximum. So it means when x is equal to 20, if I replace 20 here and 20, I obtain the maximum possible area. Given that I have to maximize the area, given the fact that I only have $320 of pence. This is the problem. I will share this problem with you later. You don't have to understand it now deeply. If you don't know, if you don't remember calculus, I mean, it's difficult that you understand. But let's summarize the session because the time is over, and this is the challenging part of teaching quantitative methods in 2 hours, which 2 hours is nothing. We could last here the whole day. I could be talking to you 5, 6, 7 hours, and even so, it will not be enough. Then let's summarize. You have statistics. If you need to collect data, you use statistics, you use random variables, you use distribution. There are many standard distributions. The normal distribution, which people call Gaussian distribution also. You have the standard normal distribution, the non-standard one. When it's not standard, it means the expectation value is not 0, and the variance is different to 1. Because for the standard case, 0 and 1. You can have discrete random variables, continuous random variables. Be careful with that difference. You can investigate correlation between variables via statistics with the coefficient of correlation. Also with linear regressions or regressions in Excel or in any other software which helps you to find correlations. The correlations are not necessarily linear, to be quadratic, cubic, whatever, exponential. The pandemic, for example, remember the pandemic. Actually, when the pandemic came, because it was the fashion, I wrote a paper about the propagation of the pandemic. For example, I found a pattern. And of course, the pattern of the pandemic is simple. It becomes exponential initially. Exponential is that it propagates so fast. But then after a saturation period, it becomes flat curve. And why does it become flat? Because all the population got sick already. So the outbreak will not propagate anymore. That's the reason of the saturation. And this saturation happens in many systems, in physics, in mathematics, in biology, etc. Then, of course, you can find the regressions which describe the kind of data you have. And after you are sure that there is a correlation between the variables and you have the function, you can apply calculus. Maximum, minimum, these kind of issues. But with the criteria of the derivative, you have to be careful. Because differentiability, of course, for a function to be differentiable, it has to be continuous. But the opposite is not true. Not necessarily a continuous function is differentiable. I will show you an example. This function here, if I have a function like this, with this discontinuity, it's not differentiable at this point because it's discontinuous. If the function is continuous, it has derivative. Differentiable means it has derivative defined everywhere. But now let's assume this case. I put a comma. This function like this, which is a comma. This function is continuous, but the derivative at this point is not defined. So I cannot use the criteria of derivatives in this point because the slope on the left is negative, the slope on the right is positive. If I calculate the derivative of this function at this point, it's not defined. So this function is not differentiable at that point, but it still is continuous. So the continuity doesn't guarantee differentiability, but differentiability requires continuity. So this is some mathematical issue you don't care. I mean, what you should care is the practical point of view. The practical point of view is that once you have the correlation between variables, you have the relation, the connection between variables, you can use calculus, you can input the data in matrices, which is what we saw just right now before. You can make tricks with the matrices, you can find eigenvalues, eigenvectors, etc. Because I mean, your research is a long-term research. I think which year are you now? First year, second? When do you finish thesis? When will you finish your thesis? Saturday, at the end of the year. So it means you have plenty of time for studying these things if you need it. First, you have to see which data. Let's do something. You need to see first what kind of data you want to collect. If it's qualitative, you can transform it to quantitative in the way how I told you. You can define a random variable, etc. And then after, if you have some question, doubts about which path you should follow, you can ask me informally, send an email, and I can reply to you. I can send you the tools which you need to learn, because in a research you don't know everything. When you do research, you don't know everything. You know a little bit, you add that, and then you develop your weapons. You start to learn, and after you start to use those weapons for analyzing the problem you have in front. Well, it will take, of course, this kind of analysis also. If you are not familiar with quantitative methods, you need to. And this currently finish the session. With this, we finish the session right now. And that's it. I think it's 9 and 10 already. I overpassed the time. Sorry about that. So see you. Well, I will not meet after, but let me finish this.